right, so I want to stress one more time that the indicators only work in the specified pH that's on your chart. So look at Rome Cresol Green one more time. What is the highest pH that it can indicate? 5.5. So I'm going to use my pH meter here. I just can dip this in a solution and it will tell me the pH. And it has to at least be 5.5. How do I know it has to at least be 5.5? Because it's blue. But it could be higher than 5.5. 5.5 is as high as it is. What do you got down there, Daniel? Can you see it? 9.15, right? But it's still blue. It's going down a little bit? Yeah.
8.98.
8.9. It doesn't say 8.9, right? But the highest it can indicate is 5, so it can always be higher than that. So on your data table for Rome Cresol Green, we need to take some before observations. So Tanner and Daniel just said that we're around 8.9 to 9.0 for our pH, our initial pH. How else would we want to make some observations about this? It's blue. How else would you describe it? You can say liquid, and you can say clear or transparent, right? I think of this as being more clear. This is more transparent. It's blue, it's transparent. There are a little bit of bubbles on the bottom. All right, since we're wanting to test the effect of carbon dioxide, I have dry ice, which is just frozen carbon dioxide, but it's super cold. So if you ever mess with dry ice, please do wear gloves because it can give your little fingers frostbite, and that would be super bad. All right? All right, so once I drop the dry ice in there, we're going to start taking some observations of what happens during, and I'll hold it up so you guys can see. What is dry ice doing right now? What is that smoke? It's carbon dioxide, it's gas. So it's going from a solid straight to a gas. Who remembers what that phase change is? Close.
Evaporation.
Sublimation. Sublimation. Straight from a solid to a gas. Right? Sublimation. All right, so I'm going to throw it in here, and we're going to watch and see what happens. Right? What do you automatically see start forming at the bottom?
Bubbles.
Bubbles. So we can write that down in our during observation. We've got bubbles. What else is at the top?
Gas.
Like a gas. What do you notice that's happening to the color? It's getting lighter, right? And it may take a little bit of time. But as this becomes more acidic based on your chart, what color should it turn into? Green and then
Yellow.
and then yellow. All right, so we're gonna let this one go for just a second, and I may have to add in a little bit more dry ice. So we'll let that one go. The vapor is really cool. Like it's cool to the touch. If you want to add that the beaker gets cold, right? Cold during the reaction. Let that go. Is it turning? Slowly. Just add another one in there for good measure. All right. Just throw some more in. Throw some more. Has anyone ever used like dry ice in their pumpkins at Halloween or something?
Oh yeah, I have.
Yeah,
It's great.
so you can buy dry ice at like grocery store, like Fred Meyer sells it. You do have to be 18, but you can use it, and you know, household experiments under adult supervision is always good, obviously. I'm gonna speed up that reaction. All right, there we go. And there's our final ending color, right? So now we have that nice yellow. So based on your chart, what is the pH at least now? 3.8 would be the low end, right? 3.8. And I'll probably have someone, once all the dry ice is done, I'll have someone come up and use the pH meter and take our final pHs. All right, universal indicator. In fact, will you be my pH man for a second? Will you find the pH of the universal indicator for me? Ready? Right. Second one right there. Xander's gonna find our initial pH. What other observation should we take for universal indicator? Purple. It's purple. What else?
Transparent as well.
Why do you think universal indicator gets the name universal, looking at that chart?
Because it spans across the whole chart.
It expands the longest way. So this one is going to provide a large amount of color change, as long as we can get it acidic enough. What do we got?
10.6.
10.6, and just so you know, you don't have to put it in about 2 centimeters next time. There you go. 10.60 for our initial pH. Does that fall in the purple range according to the chart?
Mm-hmm.
Yep. Okay. You're good. Here we go. So we'll get this one going. All right. So now we're blue. Yeah. Now we're a little bit more turquoise. What? I know. See, it goes really fast through green and yellow. There we go. So there's our green, right? A little bit more green. And whoa! There we go. Now we got some yellow going on. All right, and it'll probably stay around yellow. We might get a little bit of a dark orange. We're gonna let that one go for just a couple more seconds. We'll come back to that one because I can always add a little bit more dry ice. Based on the color now, what's the pH?
Around 6.
Around 6. Let's test it out. Where did that pH? Here we go. Are we around 6 right now? Just do like the first 2 centimeters in there.
Yeah, around 6.
Around 6. All right.
Going down.
Yeah, it should keep going down. Why is the number going to keep going down? We still have dry ice in there, so the whole reaction hasn't happened yet. All right, you're good. Do you want to go ahead and do phenol red though? Do you want to like spice it off in this? There you go. Test our phenol red for our initial pH. You can always round it.
About 9.3.
About 9.3 for phenol red, 9.3. How would you guys describe this color? It's not really red. Pink. I've heard some people argue magenta and fuchsia. You can pick whatever pink shade you decide. Fuchsia is just a fun word to write down if you decide you want fuchsia.
Actually,
What?
What is it at right now?
Both.
I didn't catch it.
Yeah.
What
All
did they
right.
say?
And
That
you
was
can like
right
combine those words and make your own color.
Yeah.
If you want to. Fuchsia.
looks like
All right, if fuchsia is going to become more acidic, what color is it going to turn? Yellow. Here we go. Some of these start going pretty fast.
Get ready.
Oh, there we go. All right, so now we're yellow. All right, turn. We got more. It's okay.
So magical.
It is so magical. All right. We'll test the final pH of that one in just a little bit. So next we have methyl red. Right now, what color is methyl red? Yellow. Xander, do you want to find our pH of methyl red?
It turned off.
Oh, just
what's the pH of the fuchsia?
we're gonna wait until the reaction is done, until all the dry ice has sublimed. 8.4 for methyl red. Would you consider this to be like a bright yellow, a pale yellow? Pale yellow. All right, so you can go with pale yellow. And what color should it turn?
What is it?
Methyl red. Pinkish white. So like maybe a light pink, all right?
Whoa.
This one went really, really fast, right? So there we go. There's our nice.
I
was
like
looking away.
Not colors. What? All right.
I look away and then when I look back, it's still.
It's magic, right? Magic. All right, our last one is brothymal blue. So Xander, come up and find brothymal blue. Yeah, you just buy some bags. It comes in a block, and I used a hammer and like beat it into like small pieces. But yeah,
9.2.
it's $1.49 a pound. Just in case anyone cares to know.
9.2.
9.2 for brothymal blue. How would you describe this shade of blue?
Sky blue.
Sky blue. It's almost the same color as the bulletin board back there. Bulletin board blue. All right, it's a bulletin board blue.
I just said blue.
And if we become more acidic, what color does it come in?
Yellow.
Yellow. And this one does go pretty fast, so don't look away this time. Don't look away.
His eyes are looking away.
Watch it not go very quick this time.
Yeah.
There we go. Pretty fast. All right, let's go ahead and get universal indicator. We're still hovering around orange, and what color should we be able to get universal indicator down to? Red. Red. If we can get it more acidic, which is not going to be that in that one. We're going to do that in this one. Right, so here I have a little hydrochloric acid, which is obviously very acidic, right? Hydrochloric acid. So if we just add some more darker orange. There we go. A little bit more of a red color. Let's just throw some more in there for good measure. All right, let's go ahead and find our ending pHs real quick, because then we have to do a little prediction for our last one. So ending pHs, brom creosote green, what do you got?
3.6.
3.6 for brom creosote green. Universal indicator,
About 2.7.
2.7, all right.
About 5.
About 5, all right. 5 for phenol red,
4.5.
4 for methyl red, all right.
4.6.
And 4.6 for brothymal blue. Thank you. You were a great pH helper. Based on, which one? Brothymal blue was 4.6. Based on every single one of the beakers, what happened to the pH? It went down, right? It became more acidic when we added in carbon dioxide. So right here, I have some simulated seawater. I went to Petco and I bought this stuff. Here, I'll show you. Because you're going to be using this for a lab you're doing next week. It's called Instant Ocean. And so you can make Instant Ocean. This is what you would use in saltwater aquariums.
I have a saltwater aquarium. Can I just do that?
I don't know. To keep it in control, we'll all use the same stuff. Right? Instant Ocean is going to give us a pH very similar to ocean water because it's used in saltwater aquariums. The ocean is a very, very delicate system, and the pH normally is right around 8.0 to 8.2, all right? So for our starting pH of seawater, we're going to write down 8.2. And the whole point of this is for us to start looking about how are these man-made greenhouse gases, specifically carbon dioxide, affecting our oceans. Based on all of the other observations we just made, what do you think is going to happen to seawater when we throw in carbon dioxide? Nothing's going to happen? Based on the other observations. Lower the pH. Do you think there will be a color change? No, because I'm magic, but I'm not that magic, right? There's no indicator in this. There's not going to be a color change, but we should about how, if the ocean water becomes more acidic, that might affect the oceans? What do you think?
Corals need a certain pH, so
All right, so fish and coral reefs need certain pHs to survive.
It may start like kind of corroding the ice in a way and causing it to melt, which will raise the ocean levels like we said we were doing before.
All right, so maybe it will speed up the melting of the polar ice caps. Any other ideas? Who had sulfur dioxide for their poster? Anyone in here do sulfur dioxide? What does sulfur dioxide make? Acid rain. And what can acid rain do? Destroy crops. All right, it has the ability to destroy things, and that includes things that live in the water. Think about putting acid on your skin. What might it do to your skin? Burn. So think about raising the acidity level in the ocean and what effect that might have. You're going to be designing a lab where you're actually testing the effects on seashells or organisms that have like a hard shell that live in the ocean. So you're going to be using different pHs of solutions and dropping in shells and watching the reaction that starts occurring between the solution and the shell. We'll find our final-ish pH of that last one. It's still going, but it's probably a little bit lower. No, the seawater. About 5 right now. So that final seawater one is 5. The cool thing about acids and bases is I made this more acidic by adding in carbon dioxide because it produces an acid, which we'll talk about later. But I can turn it back, right? I can turn it back by adding something more basic to it. So I have household ammonia. Where did you hear about household ammonia?
in our
In your ranking, right? Household ammonia has a pH of 11.9, 12, right? It is very, very basic. So if I take my household ammonia, and this might go pretty quick, and it might not stay, but if I dump it in here, I do a little swivel, right? Yeah, I did. I just did that. Magic, right?